Welcome to Calculus. I'm Professor Greist. We're about to begin. Lecture 33 on complex volumes.
Computing volumes in general is not so easy a thing to do. In fact, you're going to spend a significant amount of time in multivariable calculus worrying over such problems. But, as we'll see in this lesson, some volume problems are solvable if you put the right spin on it.
The types of objects whose volumes we can compute are necessarily limited. Most solids are too complex. However, there is a class of solids for which our single variable calculus will work. These are the volumes of revolution. That is, solids obtained by rotating some two-dimensional shape about an axis, sweeping out a three-dimensional volume. There are two principal ways to decompose such an object into simple volume elements. The first is by taking slices orthogonal to the axis of revolution and progressing along the axis. This tends to lead to disk-like volume elements. Of course, the other way is parallel to the axis of revolution. Slicing about a region that is parallel leads to a cylindrical volume element. In general, let's do some examples to see these two approaches. Let us consider the solid formed by rotating a disk about an axis. One might describe this object as donut-like. What's the volume of such an object? Let's set up coordinates so that the y-axis is the axis of revolution, and that the disk that is rotated thereabout is of radius a, and the center of the disk is located a distance, capital R, away from the axis of rotation. Then, decomposing this volume by slices that are parallel to the axis of revolution gives us a cylindrical volume element. Let's compute that volume element and then integrate. The volume element intersects this disk along a vertical strip. What is the height of that vertical strip? If we use x to denote our distance from the axis of rotation, then by building the appropriate right triangle and recalling that this disk has radius a, we see that the height of this cylinder is twice square root of a squared minus quantity x minus r, quantity squared. And thus, the volume element, being cylindrical, is what? We have to take the circumference, that is 2 pi x, and multiply it by the height, twice root a squared minus x minus r squared, and then multiply that by the thickness, dx. We integrate this to get the volume. And now we have the integral of 4 pi x square root of a squared minus x minus r squared dx. What are the limits on x? X is going from capital R minus a to r plus a. This integral is not trivial, but it's easier if we perform a change of coordinates. Let u be x minus r. We're centering the coordinates at the origin of this disk. Then we're integrating as u goes from negative a to a. 4 pi times x, which is u plus r, times square root of a squared minus u squared du. If we distribute that multiplication and split it up into two integrals, then our job becomes easier, because we note that the integral on the left has an odd integrand, that is an odd function in u that is integrated over a symmetric domain. Therefore, the former integral vanishes and goes to 0, and the only thing we have to compute is that second integral. Now, I'm going to break that up a little bit, I'm going to factor out the 2 pi r. What's left over is twice square root of a squared minus u squared du. Why have I done that? Because if I pull out that constant, 2 pi r, then what is left over is an integral that I recognize. It is an integral which computes the area of that disk, which we certainly know to be pi a squared, giving a final volume of 2 pi squared r a squared. If we repeat this computation using a volume element obtained by slicing orthogonal to the axis of revolution, then what will we obtain? This volume element is going to be an annular region consisting of some large thickened disk minus a smaller concentric thickened disk. We need to determine the radii of this outer and inner disk. To do so, let's construct, again, some right triangles in the cross-sectional disk. And knowing that these right triangles have hypotenuse, a, and height, y, then we see that the width is square root of a squared minus y squared. That means what? Well, the volume element is going to be the volume of the thickened outer disk. That is pi times quantity capital R plus square root of a squared minus y squared squared. We have to subtract the volume of the inner disk. That is the disk with radius capital R minus square root of a squared minus y squared. Now this volume element is, of course, multiplied by dy, and then algebraically simplified, we see that we have identical terms in our squares, and we're subtracting the latter from the former. So by expanding and collecting terms, we see we obtain 2 pi r square root of a squared minus y squared minus negative 2 pi r square root of a squared minus y squared. All of that times dy. Thus, we can compute the volume as the integral of this volume element, as the integral of 4 pi r square root of a squared minus y squared dy. And we see that although we're using a different volume element in a different variable, that integrating this as y goes from negative a to a yields the same integral as we saw previously. It is 2 pi r times the integral that gives you the area of this disk, leading to, again, the final answer of 2 pi squared r a squared. Now, you should perhaps be thinking at this point that it seems as though this volume is really the area of the cross-sectional disk times the circumference traced out by the center of that disk. Well, we haven't proven that that's true, but keep it in mind. Let's move on to a different example. This one, compute the volume of a ball with a cylindrical hole drilled through it, like a bead. Let's say that we set up the y-axis to be the axis of revolution, and that our ball has radius capital R, and the hole drilled has radius A. If we choose slices that are parallel to the axis of revolution, then we have a cylindrical volume element, a cylinder with radius x that varies. In this case, the volume element is 2 pi x, the circumference of that cylinder, times the height, which is twice square root of r squared minus x squared dx. Integrating this to obtain the volume gives what? The integral of 4 pi x square root of r squared minus x squared dx, as x goes from a to r. Pay very careful attention to those limits. Make sure you'll understand why that is true. Doing this integral won't be so bad with a u substitution of u equals r squared minus x squared. That leads to the integral 2 pi times the integral as u goes from h squared to 0, where h is the half height of this object, if you will. We're integrating negative square root of u du. That leads to a final answer of negative 2 pi times the integral of square root of u. That's 2/3 u to the 3/2. Evaluating as u goes from h squared to 0 gives what? 4/3 pi h cubed. We can also compute this volume by choosing a volume element that is orthogonal to the axis of revolution. In this case, those slices at some constant y are annular regions. And to compute the volume element, we need to determine the outer radius and the inner radius of these annuli as a function of y. Well, in this case, the outer radius is, through a right triangle computation, square root of r squared minus y squared. The associated area of that disk is pi times that quantity squared. When we subtract off the area of the inner radius disk, that's removing pi a squared. This times the thickness dy gives the volume element. We can simplify that a little bit using what we know about this height, h. This yields the volume element pi times quantity h squared minus y squared dy. And thus, computing the volume as the integral of the volume element yields pi times the integral of h squared minus y squared dy, as y goes from negative h to h. This is a simple integral, yielding the same answer as before, 4/3 pi h cubed. Remarkable in that a and r are not explicitly stated. Let's do one last example. Compute the volume of a vase formed by rotating the curve x equals square root of sine y plus y over pi about the y-axis, as y goes from 0 to 2 pi. Using a orthogonal slice yields disks as the volume element, disks of radius x. Thus, the volume element is pi x squared dy. Substituting in our function for x yields pi times quantity sine y plus y over pi dy. Integrating this to obtain the volume as y goes from 0 to 2 pi gives a very simple answer. We get negative pi cosine y plus y squared over 2, evaluated from 0 to 2 pi. I'll let you compute that the volume is 2 pi squared. Now, when you're doing homework problems on volumes of revolution, there are a couple things to keep in mind. The first is that there's no one formula that will do all volume computations for you. You're going to have to think about how to decompose your region. Always think in terms of whether you're slicing parallel to or orthogonal to the axis of revolution, and that will inform what you use for the associated volume element.
This ends our introduction to volume in this dimension. In our next lesson, we're going to be a bit more ambitious. We're going to ascend to higher dimensions, introduce higher dimensional shapes and volumes, and show how calculus can make sense of the geometry of the fourth dimension and beyond.